Welcome to this explainer. As fans of geotechnical engineering, we know we don't just build on top of the ground, we build into a living, breathing matrix. Today, we're looking way past the foundational basics to unpack the real, hidden memory of the Earth. We're diving deep into the compressibility and consolidation of soils.
It's the ultimate engineering challenge, right? When we drop a massive structure, like a towering skyscraper or a sprawling highway onto this matrix, what actually happens microscopically? Well, to answer that, we've got to zoom way in.
Okay, let's dive into this. Here's our roadmap to demystify how the Earth behaves under immense weight. We're going to hit 1. The matrix beneath our feet. 2. Compaction versus consolidation. 3. The mechanics of time. 4. Soil has a memory. And finally, 5. Measuring the squeeze. Let's get to it.
Section 1. The matrix beneath our feet, the hidden structure of Earth. We really need to shift our perspective here, because as engineers, we aren't building on a solid block of matter. We're building into a complex, hidden structure.
You see, soil is a particulate material. It's essentially a mix of solid soil grains and the void spaces between them, spaces that are filled with air, gases, water, or other liquids. When we place a massive load on the ground, the solid grains themselves, they don't really shrink. The deformation happens primarily because those void spaces get squeezed.
And that brings us to compressibility. By definition, it's the property of a soil by virtue of which volume decrease occurs under applied pressure. Sure, soil can deform elastically and sort of bounce back, or it can deform plastically and permanently bulge out. But it's this compressive deformation, literally the shrinking of those void spaces, that keeps engineers up at night. Because a volume decrease in the ground absolutely means settlement for the building right above it.
Section 2. Compaction versus consolidation, the two ways soil shrinks. So we know the soil is getting squeezed, but we need to shift how we categorize this squeezing process, because it actually happens in two distinctly different ways.
We've got to separate how this squeezing happens into two distinct camps. On the left, we have compaction. This is an artificial mechanical process. Think of vibrating rollers intentionally packing the dirt to expel air. It's super fast. But consolidation on the right, that's driven by static pressure, like the natural, continuous weight of a building. And crucially, consolidation expels water, not air. Think of it like a sponge. If you squeeze a dry sponge, the air escapes instantly. But put a heavy book on a waterlogged sponge, and it takes time for the water to slowly seep out. That is consolidation.
So, the absolutely crucial point here is understanding exactly what happens the instant a load is applied to a saturated soil. And this brings us to a fascinating geotechnical concept, the Skempton B parameter. For a fully saturated soil, this parameter is nearly exactly 1. What does that mean for us? Well, it means when you first drop a massive weight onto saturated ground, the solid soil grains don't feel the extra stress immediately. Because water is practically incompressible compared to the soil skeleton, the pore water takes almost 100% of that initial stress. It's only as the water slowly, agonizingly escapes that the pressure transfers over to the actual soil grains, becoming what we call effective stress.
Moving right along to Section 3, the mechanics of time, why soil behaves like a sponge. Because if consolidation is all about water escaping, then the speed of that whole process is entirely dictated by the permeability of the soil.
This is where the specific type of soil becomes incredibly important. Sand, for example, is highly permeable. It has relatively large void spaces, so when you load sand, the water shoots out and the sand compresses almost instantly. But clay is incredibly dense. The particles are microscopically flat, and the void spaces are ridiculously complex and tiny. Water struggles immensely to escape through those microscopic pathways, so under pressure, clay takes its sweet time.
To put a real number on it, an undisturbed clay sample in a lab requires a minimum of 24 hours just to fully consolidate under a single load increment. Out in the real world, it can take decades. Just look at the Leaning Tower of Pisa. That underlying clay layer took centuries to slowly squeeze out its water and finish settling.
Which brings us to Section 4, soil has a memory, reading the Earth's past. This is arguably the climax of our explainer. We are diving into the absolutely fascinating concept that soil retains a physical, readable record of its geological history.
We start with what engineers call a normally consolidated soil. This is a soil layer where the weight sitting on it right now is the maximum effective stress it has ever been subjected to in its entire stress history.
If you have a normally consolidated soil and you decide to build, say, a new factory on it, you're adding unprecedented weight. Because the soil has literally never felt this pressure before, it's going to undergo significant void ratio changes. The water will be squeezed out, and you will definitely see substantial, brand new settlement.
But history changes everything. Imagine that thousands of years ago, a miles-thick glacier advanced over a plot of land, applying immense, crushing pressure. Then, the Ice Age ended, the glaciers receded, and that heavy load was lifted. That soil is now what we call over-consolidated. Nature essentially pre-squeezed it. And by the way, human demolition of old, heavy structures does the exact same thing. The soil has a literal physical memory of that heavier past. So if you build a modern structure on it that's lighter than that ancient glacier, the soil won't settle nearly as much, because it's already been compressed by history. How cool is that?
Okay, let's move to our final section, measuring the squeeze, how engineers predict the future. We've talked about these massive geological concepts and slow-motion underground water flow. Now, how do engineers actually bring this all into the precise environment of a laboratory to predict the future?
Well, it all starts out in the field. Engineers have to carefully extract an undisturbed sample from deep underground at a specific depth, which we'll call Z. It is absolutely critical that the structural arrangement of the soil particles isn't ruined during this extraction. If it gets messed up, the laboratory tests simply won't reflect real-world behavior.
Once they get that pristine sample back to the lab, it goes straight into a consolidometer, or an odometer. This nifty device allows engineers to safely, systematically, and precisely simulate the immense pressures of a future building. They apply predetermined stress increments, basically adding weight step by step, and they carefully measure two things: exactly how much the soil compresses in total, and the time rate, meaning how long it takes for that compression to happen at each step.
And the results from this give us a compression curve. The steep virgin compression curve shows the soil experiencing new maximum pressure for the very first time. But when engineers remove the pressure, the rebound curve shows the soil swelling back up just a little bit as it tries to suck water back in. Notice, though, it never goes back to 100%. The soil has been permanently physically altered. Its void ratio is forever changed, and its memory has been rewritten.
As we start to wrap up, it is crucial to remember this quote from the source text. Consolidation is a relative term and does not refer to the stiffness of the material. You see, consolidation is purely a measure of the degree to which the process of water escaping has advanced. A highly consolidated soil isn't necessarily a rock-hard soil. It just means the water that was going to be squeezed out by a certain weight has finally finished leaving.
Which leaves us with this final thought. Depending on the clay content of the soil, the weight of the structure above it, and the hidden geological history of your local area, the ground doesn't just settle once and stop. It is a slow, gradual, time-dependent phenomenon. So how much is the ground beneath your own home still slowly consolidating, expelling microscopic drops of water right this very second? Thanks for joining me on this explainer, and keep questioning the world, even the parts you walk on every single day.